Hello everyone, my name is Fadi and today I will be presenting this webinar on high strain rate tension testing of lightweight materials for automotive crash simulations. Before I start, I would like to thank Zwickol for the opportunity to present at the virtual testing forum for this year, and I would like to also thank you for attending this webinar, and I hope you find it informative and useful. Very brief introduction about us at Fadi AMT. We perform advanced material and component testing with advanced sensors such as DIC and other optical metrology techniques. We've been doing this since 2016. Our approach is to couple state-of-the-art facilities with highly skilled personnel. We do believe that our personnel have to have intimate understanding of material deformation in order to perform testing so that we can understand what the material is doing during these mechanical tests. On top of that, we couple almost everything we do with digital image correlation and other optical metrology techniques in order to maximize what we can get out of these mechanical tests. And the ultimate goal is to elevate the outcomes of what we call conventional tests, in addition to stretching the limits of what can be done in terms of mechanical testing to go into specialized and custom testing solutions. The types of tests that we perform, they're different, wide-ranging, from the simple tension to the complex multi-axial or biaxial and so on. These are just simple examples of what we do mainly for the automotive sector, but we also do it for other sectors as well. I picked a video, or I chose a video to sort of give an example of the kind of testing that we do. And for this, I'm showing this advanced biaxial test. And the reason I called it advanced is because typically biaxial tests are not really straightforward. On top of that, this particular test was done in a bulge mode on a 4-micron thin foil, very extreme condition or very extreme material state. And you can see from this video that we're coupling strain measurements with digital image correlation, obviously, with other sensors, such as a high-resolution pressure sensor, in order to completely describe the response of the material, basically stress and strain. As I mentioned earlier, the majority of our work is with automotive OEMs and suppliers and material suppliers, but we also work with other sectors, including other transportation sectors. So now back to the webinar and our topic of high strain rate tension testing of lightweight materials and how do we use that for automotive simulations, mainly crash simulations. To start here, we need to talk about why is this topic important? Why do we need such data at intermediate and high rates? And for that, I'm going to go back to the basics of mechanical testing, the humble tension test, which is performed almost everywhere. Everyone is familiar with it. This is a classic electromechanical machine with a classic dog bone sample. We typically pull the sample to generate a stress strain curve as such. And from there, we fit it to an equation, a mathematical equation, or simply feed it directly into our finite element model in order to perform finite element simulations. This is the standard process that is predominantly done at quasi-static rates, obviously because most of the tension testing that we perform is done at quasi-static rates. The question is, can we take the data from such a curve to simulate all events that involve material deformation? And to answer this question, we will go and focus on metals in the transportation sector, maybe automotive, and try to look at two very important events: the forming events, and second is crash events. So if we take a closer look at forming scenarios, we have stamping, progressive stamping, machining, forging, and so on. All of these forming events typically involve material deformation at rates that are higher than quasi-static. In some cases, actually, they're almost into the high rate regime, such as machining. When we go to the second type of events, which in this case we're talking about impact or crash events, that's obviously extremely fast. Material will deform at very high rates, regardless of what application we're talking about here. And we have a variety of crash events here in this slide or picture. So obviously, in order to accurately account, in order to accurately simulate such events, whether it's forming or crash, we need to accurately account for material behavior. Therefore, we have to basically address this issue. We need data at speeds that represent the speeds or strain rates that are seen by the material under forming and crash simulations. And I put in this slide just some general ranges of strain rates that we typically see for such events. For forming, we are typically between zero point 0.1 and 1, sometimes higher strains per second. And obviously for crash, we could reach hundreds, if not thousands, sometimes of strain rates per second. Therefore, we do need data at higher speeds in order to feed into these models. And this is not only true for metals. This is exactly the same for other materials such as composites or composites and polymers and other engineering materials. So how after basically we talked about, okay, we need this data at intermediate and high speeds. The question that usually comes is like, okay, how critical is it? I mean, how far off are we if we just use quasi-static data? And that invites a topic which we call rate sensitivity. How sensitive is a material to strain rate or deformation rate? And the answer is complex, but I chose basically a couple of examples to try to answer this question. Most materials exhibit, at the very least, notable rate sensitivity to deformation rate. And this set of curves that I'm showing here as an example, this is for a steel grade, for an automotive steel grade, and you can obviously see that the stress and the strain levels are both affected by the speed of the test or the strain rate of deformation. We could potentially say, okay, looking at the curves, we can see a systematic increase in stress as a function of strain rate. So maybe we can guess it. Maybe we can just do one test at quasi-static rates and then somehow scale it upwards per speed. That might be okay or sounds simple enough, but in reality, it's not that straightforward, simply because we have to establish this relationship between the increase in stress and strain rate. And also, and more importantly, most or some materials do not behave in such a clean, systematic manner in terms of rate sensitivity. The curves on the right-hand side now, you can see that the level of increase of stress as a function of strain rate is not linear in any shape or form. On top of that, we have some rotation in the stress strain curves. We don't have the same level of strain hardening, which changes also with speed. So between these two cases, where you have some materials that are relatively gentle and systematic in their behavior and could be somehow extrapolated from quasi-static to dynamic or high rate, you have some materials that cannot be described by systematic and they're more complex. Therefore, it is always important to obtain the data at high rates. Then comes another question that we sometimes hear. Okay, maybe the material is sensitive, but my process, for example, is a stamping process and I know exactly the strain rate. Maybe it's just 1 strain per second. Can I just go and generate a stress strain curve at that speed and be done with it? Instead of generating all these curves at 5 or 6 or 7 strain rates? And the answer is complex, but to simplify it, we go to the finite element domain. And this is an example of a dog bone that is pulled in tension in a finite element, basically, model. And you can clearly see that the different elements in the mesh are seeing different colors, which represent different levels of strain. And so you have some elements that are barely deforming or not deforming at all, and some elements that are in the necking zone deforming a lot. So if you calculate the strain rate of the elements in this particular model, you will see them ranging from quasi-static to whatever, to higher strain rates. So the different level or the different elements are seeing different levels of strain rates in the same exact event. And therefore, you cannot really describe all the elements or the deformation of all the elements with one curve. A more complex scenario is basically an impact event, and this is just a simulation of an impact event. So we have an impactor of a certain shape hitting a sheet, a flat sheet, and you can clearly see from this simulation you have so many elements that are technically blue, barely zero deformation or almost zero deformation, and then you have the green and the red at the corners. And if you take that strain and you compute the strain rate, of course, it is varying or different for different elements. Therefore, if I were to execute this simulation correctly, I have to provide sufficient number of curves that describe the behavior of all the elements here. And that's another reason why we typically talk about not one single curve at a particular speed. We typically talk about several curves to cover a full range or a particular range of strain rates that describes the entire event or the entire process. So now we go from, okay, maybe we agree that such data at intermediate and high rates is important, and generating it for at least a range of strain rates is important, if not the full range. How do we generate such data? There are multiple approaches, and I just listed here 5 of the common ones, or at least the known ones. Um, these 5 approaches, they have different applications to some extent, but if we were to take a closer look and see, can we achieve what we want with all these approaches? I'm going to start from the third and fourth ones, which are the drop tower and impact testers. By nature, or from the name of these tests, they're not technically designed for obtaining stress strain curves. You know, the drop tower is mainly for components, and then impact tests are typically designed for obtaining energy up to the point of fracture. The same thing with drop tower. It's basically energy up to fracture for a component and so on. So they're not really designed for obtaining stress strain curves. That being said, of course, you can instrument them to get some stress strain curves. That is not impossible. It's just that's not the main purpose, and you have several limitations on the mode of deformation that you can achieve and also the strain rate range that you can achieve. So these are not the best options, if I may say so. Then we go to some niche approaches, such as electrodynamic and others. And most of the time, when you go to niche approaches, whatever that approach is, it is niche by nature. It is typically complex, it's typically expensive, and so on, and addresses maybe certain elements of the problem that we have. I personally find the top 2 choices are the most common, of course, in the literature, and maybe the most relevant for our discussion today. So that's why I'm going to focus on them for a couple of slides to describe the differences between them and how do they compare to each other. They're very popular. Almost everyone who works in this domain, high rate deformation, should be familiar with the split Hopkinson bar or the Kolsky bar, and of course the other approach is the high-speed servo-hydraulic systems. Before we talk about them in details, I just wanted to mention that you typically see more of the Kolsky bar in North America, especially in universities, versus the high-speed servo-hydraulic systems are more popular basically in Europe and Asia. So let's talk about them in more details. The split Hopkinson bar, basically this is the simpler approach, very popular academic approach, and this is an example of it. And if you're interested in the details of how it works, basically it operates on the principle of a pressure wave that is used to deform the material sample. It can be done in compression or tension. It's a classic approach. And like I said, it is very popular in the literature, especially in North America. So there are lots of papers about the Kolsky bar or the split Hopkinson bar. On the right-hand side is an example of a modern high-speed servo-hydraulic system. And as we will show later in the videos, and probably you can see it from the picture, it is nothing but a machine that looks like a standard tension machine to some extent. However, this machine, of course, is servo-hydraulic, and the fact that it's high speed, that means basically it's configured for high speed operation. That means it can move fast, which means accumulators to enable it to go to high speed, and of course, high speed data acquisition system and other changes. So in principle, it looks like a standard tension machine, but of course, it is different to allow it, or it has many differences to allow it to go to high speeds. So that is the general difference between the two systems. Now let's go to comparisons, and this is just a personal survey of what I believe is the plus and minus, or the pros and cons of each of the two systems. Let's take them maybe one by one. From the top, as I mentioned, extensive literature on the split Hopkinson bar in most academic papers. We do see some of those for the high-speed servo-hydraulic systems. but maybe less popular. So you are able to find it not maybe as easy as the split Hopkinson bar. In terms of the system itself, the split Hopkinson bar or the Kolsky bar is relatively simple in terms of construction and operation and relatively inexpensive. And that's why most of the time these setups are built in-house, as I mentioned earlier, by research institutions and universities. This particular example, I borrowed it from our colleagues at NIST when we worked together several years ago, and you will find multiple other examples in the literature. On the right-hand side, when we go to the servo-hydraulic systems or the high-speed servo-hydraulic systems, in principle, as I mentioned earlier, it's a tension machine that just goes faster. In reality, it's a little bit more complex than that, and therefore it is expensive. So this more broader picture that I'm showing of the entire system to some extent, because it's a servo-hydraulic machine, of course, you need a hydraulic pump, and because of that, you need that chiller, which is usually outside. So that's basically an additional component, and you have the load frame itself that you can see on the far right, and the load frame, as I mentioned, this is a high-speed servo-hydraulic system, so that's why you see all these accumulators on the top to allow it to go to high speeds. And then you have the controller and the high-speed data acquisition system. So you can see the system itself is complicated, large, and therefore it is expensive. And this is one of the main reasons why we see less of the high-speed servo-hydraulic systems compared to the Kolsky bar. Then we go to the technical differences. Kolsky bar, or the split Hopkinson bar, is known in the literature to produce very good results at high rates. And these are some of the results that we obtained with our colleagues at NIST 5-6 years ago. At a strain rate of 500, which is relatively high, you can see the curves are relatively good compared to what is known in the literature for the high-speed servo-hydraulic machines. The general stigma is that such machines generate bad results. And I'm showing one of the examples of a curve that we obtained at a high speed in our earlier runs with high-speed testing. And I will be referring to the work of my ex-PhD student, Rakan Al-Turk, a lot in this webinar. And we will borrow some of our earlier results, especially the bad ones, to show basically what you could potentially see or what you know from the literature that the data is not necessarily good. So we will come back and address this issue, but this is a main technical issue. And there are so many people that I've spoken to who do not believe in high-speed servo-hydraulic systems because of this. They consider them waste of time and money because they're not good. And hopefully we will change that today. Then we go to even when you optimize and refine and see some good work on high-speed servo-hydraulic systems, you tend to see decent curves at low speeds, but then as you push the speed higher, the deterioration of the quality is very fast. And I'm showing again some of our previous results where you can see when we go above 1 meters or 1 meter per second, the quality of the curves gets really bad. Let's go to another aspect. And now we talk about the sample size. At least for me personally, I describe it as such. With high-speed servo-hydraulic systems, you are able to go with relatively larger samples than Kolsky bar. And on the left, I'm showing one of the largest Kolsky bar samples that you will see in the literature. This is one that we used again with our colleagues at NIST, and it's relatively large. But that is almost the max that you can do with typical Kolsky bars. And that's why I usually say the size of the sample is on the miniature side when you talk about Kolsky bar samples. With servo-hydraulic machines, you technically can do larger samples. You can literally put a full-size sample if you want a standard ASTM E8 or ISO 6892 sample, if you wanted to on such machines, because the size is not a problem. So that's why I always say in this kind of testing, high-speed servo-hydraulic systems, it allows you to go to the, at the very least, to the sub-size sample versus miniature. And that is a better representation of material behavior if you really care about that. Next comparison is a problem that is known with the Kolsky bar. Again, when we talk about deformation by this pressure wave that's generated, this wave has a certain length and duration, And in most cases, if you're dealing with a highly ductile material or even just decently ductile material like a mild steel, your wave will likely sort of fade away before you finish the test. And here's an example of a test where you can see basically the sample is deforming and then all of a sudden it stopped. The wave basically, the prime wave has finished its job and the sample is still not, hasn't fractured basically. And now you can see in the video that there's a second wave coming, which is the rebound wave, or um, the second, and there's a third wave, and so on, that will deform the sample further and further, and ultimately it will fail. But from a stress strain perspective, you can only use the curve that's generated by the prime wave, and that usually leads to an incomplete stress strain curve. In comparison, when we go to high-speed subhydraulic systems, there is no lack of force, there is no lack of displacement or travel. So you typically pull the entire sample to fracture in one shot and you produce the stress strain curve. And I'm showing here an example of a stress strain curve that goes to about 40% ductility, no problem. And of course, I'm showing you a preview of a good stress strain curve. This is just a quick early view of a decent stress strain curve that was obtained at 1,000 strains per second, and we will come back to how we can obtain such curves. Last but not least, the main difference between the two systems is the range of strain rates. A Kolsky bar by nature is limited to a very narrow range of strain rates, typically on the high side. Your typical setup would be mm, targeting maybe 200 to 1,000 strains per second. You can bring it down, but when you bring it down to the hundreds or the teens, sometimes I've seen some of them that are really designed to achieve a strain rate of 50 or 40 or 20. The range around them stays very limited. So that's why in my diagram here or schematic, you can see I put like a standard Kolsky bar between 200 and 1,000 or 2,000. That's what you typically see or hear about or you read about in the literature. In comparison, a high-speed subhydraulic system can cover a very, very wide range. And I put here, typically, you should be able to have a small overlap with quasi-static rates and then go all the way to 1,000 strains per second, sometimes even higher, with one machine, one setup. And that is a very big advantage, especially for the automotive sector. That leads me to the outcome of this comparison. And again, this is just a personal summary or personal set of conclusions for me. Um, the advantages of high-speed subhydraulic systems, um, to me, they overweigh the limitations, or at least overweigh the advantages of the Kolsky bar system, and that's why we chose to go in this direction. They cover the full range of strain rates, and that is very important to us. We like the idea of getting all the all the curves from a similar approach or as the same system, even the same sample geometry, and you cannot do this with the Kolsky bar, and that's a big advantage. The second advantage is the fact that we can go with larger samples, so we can better represent the material that we're testing, and also we can always be sure that the stress strain curves are complete, full, so we can get the full stress strain response of the material at different rates. And on the top left here, again, another quick a quick preview or a sneak peek at some of the high quality data that can be obtained with these systems to break the, I don't know what to call it, the myth that such machines cannot generate good data. And again, we will come back to this later on. So when we put everything together, we decide to go in this route, the high-speed subhydraulic systems, because we feel, again, that they are the better choice for us, at least, based on the advantages. Now, that leaves one big problem, which is the bad results. This is documented. You can see it in multiple papers in the literature. So we accepted this and we decided that with some investigation that we could potentially try to improve that. So we still would like to go in this direction, and our approach was to go in this direction and try to address some of these problems to generate better curves and break this bad stigma with these machines. Let's take a closer look at what kind of problems are we talking about for high strain rate testing with high-speed subhydraulic machines. We have ringing, a very big problem, very popular in the literature. You will almost see it in every publication about high-speed testing with servo-hydraulic machines. And ringing is basically what you see on the top left here in this diagram. The curves at high speeds are all basically wavy, and um, most of the time you really cannot get a clear image of what the stress strain response is. So that's ringing, major problems. So we have to address it. Then we have problems related to the IC, the limited resolution of basically the measurement because of the camera, and the limited number of the DIC points, also because of the camera, because at those speeds, the resolution is limited, the number of frames is limited. So that represents a set of challenges for high-speed testing. And then we have other problems related to the actual physical test itself, reliability, reproducibility, and so on. For today's webinar, we decided that it's impossible to cover both the mechanical, I call them problems, or the system problems, and then the IC problems. We decided to leave the IC out today because we have another webinar focused specifically on the challenges of high-speed testing, or DIC applications in high-speed testing. And today we will just focus on ringing and other issues that are encountered here in order to generate some good data. So let's talk about the details of these problems. This is at the bottom of this slide, you can see the overall range of strain rates that we try to cover, from quasi-static to intermediate to high rates. And for a high-speed servo-hydraulic system, especially a modern one, you should be able to cover all of them, or the entire, basically the entire domain in a couple of modes. So basically two operational modes. The first one is closed loop control up to a certain speed or strain rate, and then you have to go to open loop control. And I put here, roughly speaking, this is at least for our system. Most systems are similar, but you could be a little bit off from there. But roughly speaking, up to about 20 strains per second, you can go closed loop. And then above that, which is the upper intermediate or high rate, most likely you'll have to do it in an open loop control. So let's talk about the different regimes and the challenges. The first regime for these machines, which is the high quasi-static, typically there's not a problem, or there isn't any problem. It's just like any other machine that you've used, except that it's a servo-hydraulic machine. So it's not going to be as, what do we call it, accurate as an electromechanical system, but it just behaves like a servo-hydraulic system. So you will get some curves, good curves, just like the ones that I'm showing on the right-hand side. And typically, there's not really a major issue. We just say you have to take care of the typical items you take care of in a normal tension test. Just your sample, your load train, force measurement, and if you're using the IC, of course, just take care of it just like you do in a quasi-static. Let's go to the second regime. When we enter the second regime, which is basically the intermediate strain rate, we see a couple of issues. The first one is something you will encounter regardless what your system is. It depends actually from system to system and from material to material. But this is a problem where you encounter this because of the speed of the piston gets to a certain point. I call it like, a funny point in the system domain, where you are talking about a large cylinder, hydraulic cylinder, and you have some oil in there, and you're pushing this piston not too slow, like quasi-static, where you don't have any problem, not too fast, like high rate. In the intermediate range, this fluid slushing while you're moving the piston, it basically interferes with the motion of the piston, so you can see clearly waviness and a significant change in the speed of the piston. You cannot really control the speed of the piston that easily, and that leads to kinks in the load displacement curve. And if you, or the load time curves, that's where you can clearly see it. And I'm showing here an example of raw data obtained for one of those tests. And you can see that the piston, we set the speed to a certain value, and then when the machine started moving, it couldn't maintain that speed. So basically we lost the speed, and then of course the closed loop control tried to bring it back up and so on. But this behavior, you cannot really stop it. It's not really a control problem. It's a problem of you hitting the resonance frequency of your hydraulics, basically. So it's, I call it, to me, it's the ringing in the intermediate range, because it's somewhat like ringing at high speeds. It's just caused by a totally different resonance. It's not really the load train resonance, it's the hydraulic resonance. Now, how do we solve this problem? You can play with your control parameters or controller parameters to try to improve it. And like I said earlier, this is a system related or system dependent. So for each system, you have to tweak as necessary. But one easy solution, if you don't really care about the elastic region, which is typically not the case, or which is typically the case for high-speed testing and intermediate testing, we don't really care about the elasticity, we care about plasticity. These loops can be removed by simply doing a good job in terms of coupling the strains coming from the IC with your load coming from the machine. And you can get rid of all of them, and you just see basically a smooth stress strain curve when you do that. The last point that I have to indicate here is sometimes, and I do this sometimes, is you must avoid that bad spot on this scale basically for your system. For example, if 5 strains per second is the worst spot for you, you can go to 10 strains per second, because from a material deformation perspective, it doesn't make any difference. So if you have a bad resonance response at a particular strain rate, sometimes the only solution is to either play with the controller parameters or your sample geometry. And if you cannot change that, then just basically avoid that point altogether. Let's go to the harder domain, which is the high speed or the high strain rate. Now we have several problems. Let's remember here that we are operating mainly in open loop control. So you really need to do a lot of trial and error to understand how the system works. And parameters need to be tuned. Usually you have to change some parameters from material to material. You cannot really do all materials at all speeds with the same kind of configuration and settings. One problem is basically the speed itself. This is open loop, and this is usually fast testing or high speed testing, which means the parameters of how you perform the test. And let me focus on one particular item here. This is in regards to at what speed and in what kind of acceleration profile do you impact your sample. So typically you want to accelerate your piston to a certain point in order to achieve a certain speed. And that is basically done by your control parameters and how you set up your acceleration profile. For hard materials versus soft materials, you want that point of impact. So the moment at which you impact the sample will change from soft material to hard material in order to achieve near constant speed. And on the right-hand side here, I'm showing 3 different curves obtained for 3 different speeds for the same exact machine, the same exact sample. And you can see the variety or variation in speed of the piston goes higher with speed. And so I cannot really use the same parameters. So I have to adjust those parameters in order to maintain a near constant speed close to the target that I'm asking the machine to perform. And that's why, like I said, this domain or this regime requires a lot of trial and error. And when you go from aluminum or magnesium to high strength steel, that will require definitely a change in your approach of when do you impact the sample with respect to the acceleration curve of the material that you're testing. And as I mentioned earlier, there's a lot of adjustment and a lot of trial and error that is needed here. And ultimately, you can achieve a near constant speed for the test that will take care of this problem. Then we go to a more serious problem, which is ringing. Ringing is basically, you can read about it a lot in the literature, but in essence, when the piston flies at a high speed and then impacts the sample, now you're generating a shock wave or a wave that propagates through the load train. And the load train is basically the sample, the grips, and the shafts, and all of that, all of the mechanical components down to the load washer, which is your load cell. It's not a standard load cell. Obviously, in these kinds of machines or systems, we use a piezo cell or a piezoelectric load cell or load washer. And so that wave, the shock wave, when it's generated, it propagates through the load train at the speed of sound, and that interferes with the load signal that is measured by the load washer or the piezoelectric load washer. And so the output of this is something that looks as bad as the curve that you see on the right-hand side here, just basically a bunch of waves. That's just what we call ringing because of this waviness in the load time or load displacement curve, whatever it is. This is a major problem because when you go to high speeds and you get such curves, you really can't do much with these curves. Some people apply filters and algorithms to sort of find the median between all of these peaks. But in all honesty, we find this approach not acceptable because it's not really good enough. I mean, with a curve like this, how could you represent it with a median curve? So this problem has to be addressed first, mitigated or at least alleviated, and then you can apply filters if you're close enough to a smooth curve. Now, there are multiple issues with this problem, and this is mainly driven by um, your machine basically operating close to the natural frequency of basically the loaded train. When your deformation rate or speed is approaching that resonance frequency of the system, you have this problem. And so your solution has to be driven from the problem itself, and that is to change the natural frequency of your load train or at least push it higher. And the general approach to push it higher is to increase the stiffness and reduce the mass, as simple as that. And so anything that can be done to increase the stiffness and reduce the mass will push the natural frequency or the resonance frequency of your load train up higher. Therefore, you can get better curves at that desired speed. It's as simple as that. And you can go into the details of this because there are so many aspects of this that can be addressed one by one. Most of those aspects are not straightforward. It's not something that you can change for this particular material sample, for example. No, there are some hardware changes that have to be done, and we talk about them often in such webinars, which are to optimize your load train, to optimize the mass of your components, grips, slack adapter, and so on, and to optimize your sample geometry. And that's what I mean by the first line here in my slide, which is to optimize your load train and sample geometry. It's very critical. You have to spend a lot of time with your system to get to the best case scenario for that particular geometry that you're trying to test or that material that you're trying to test. Once you've done all that optimization, of course, you're not going to eliminate all the ringing in your system because obviously, as I mentioned earlier, all what you're doing is you're just pushing the natural frequency of the system higher. You're not eliminating anything. So now this first item will help you improve the quality of the load signal. But then you might have to go to strain gauging. And strain gauging is just a direct solution to the problem um, by basically using the sample itself as a load cell instead of using your Kistler load washer or piezoelectric load washer. And what strain gauging does is basically reduces the length of your load train, and that increases the natural frequency of that particular part of the load train. And that usually leads to a significant improvement in the quality of the data, as we will show in a little bit. After you do those two main steps, or these two main items will help alleviate the problem, then we go to other factors that will help, which are damping. This usually helps, and then ultimately you can do some filtering and smoothing. High frequency filtering, we typically say that it's not really a bad idea once you make sure that you remove the major source of the problem, which is ringing. So I'm going to break this regime 3 into two sub um, segments and show the challenges there. Up to about 100 strains per second. So it's the first half of the high rate regime. This is an area that we feel from our personal experience that it can be improved significantly without even having to go to strain gauging. So basically, if you focus on optimizing your load train and sample geometry, which is the first item we mentioned earlier, you could potentially improve the curve to the level that is considered acceptable without having to do strain gauging, because strain gauging is considered to be painful, expensive, time consuming, and so on, and annoying, to be honest. So I'm showing here on the right-hand side a very, very, very simple example. We will show more later on of what can be done with this kind of optimization of your load train and sample geometry. You can alleviate a little bit more by tuning and damping, and you can get some good curves. And here's an example. Sorry, here's an example of a fantastic curve that was obtained without having to go to strain gauging at 50 strains per second. This is just raw data extracted, or this is a snapshot from the machine software. So it's just basically pure raw data that shows good quality without having to go to strain gauging. When we go to the upper part of this regime, from again our humble experience, we don't think that you can get anything decent without having to strain gauge. So you must strain gauge, you must do the optimization first. That is given, and then you have to use strain gauges to replace the piezoelectric load washer that you have, because it will usually generate useless data. Strain gauging is another topic we talked about in a previous webinar, and you will find lots of data about it in the literature, where and how to strain gauge. But in general, you just think of it as simple as that. You can see on the right-hand side an image of a sample, and you can see the strain gauge is placed in the grip region, and that is basically used to measure the load um, during the test. After that, you still have to do um, some tuning and damping, and that will help you achieve much better quality curves than the green one I'm showing here. The green one is just a starting point after some optimization, tuning, and so on. This is one example of one of the best curves that we obtained for high rate testing at about 500 strains per second. You can see the difference between strain gauge data and then the load washer data, and obviously clearly the orange curve is fantastic and definitely produces the quality that we want. Now for the entire range of regime 3, we can see two examples again put together of good data that can be obtained with proper optimization of your system, load train, controller, and also with the right procedure of strain gauging and so on. Again, on the left is that curve at 50 strains per second. On the right is the curve that was obtained at 500 strains per second, which is typically the upper of the range that's requested by automotive. Most automotive OEMs request the highest strain rate to be 300 to sometimes 1,000. So 500 is somewhere up there. Now, you can see from what I've been talking about, whether it's ringing or these issues with the load displacement curve, we've been focused on the load part of it, not on the strain or the deformation part, because that's usually the problem with ringing and related. So once you solve the problem or alleviate the problem with your load measurement, which is the vertical axis of your stress strain curve, the remaining part is the x-axis, and that x-axis can be taken care of by the proper use of the IC. And as I mentioned earlier, this is going to be another topic for another webinar where we talk about the proper measurements of strains with DIC at high strain rates. But once that is taken care of, you can combine the two together to get a good stress strain curve. Now, let's go to some demos and maybe more details about the actual high-speed servo-hydraulic system that we're talking about today. So first, we wanted to give you sort of a tour of a modern high-speed servo-hydraulic system to see the main components, how does it work, things that you have to pay attention to or what you should be working with, and so on. However, for the lack of time, we decided to record that video. It's about 10-15 minute video, and not play it today, so that you can play it on your own. If you go to our website, that video is a separate video, and you can play it, and it will show you basically close-up views of the main components of the system, especially where you basically do the actual testing, the slack adapter, the load washer, and so on, the sample, and so on. So please feel free to visit the website and watch that video. But for today, I wanted to play one or two videos that show a demonstration of how an intermediate or high-speed test is run, mainly how these machines operate Of course, in principle, it's pretty simple. The details are, of course, complex, but from a demo perspective, I wanted to start with a video. Obviously, I left the audio of the system still running, so you can hear the hydraulic pump running in the background, so you can feel it. The system is already configured here. The sample is already mounted, and when we start the test, the machine will try to preload the sample to detect a certain level of loading, and then after that the machine will retract downwards, and that is in order to build the right slack needed for the machine to achieve the speed that we set it to, and then after that it will impact the sample by going vertically upwards. So I'm going to replay this video again. And again, this is in the middle, that's the slack adapter. It allows the piston to accelerate to the right speed of the test. In this case, this was a relatively moderate speed, 50 strains per second, corresponds to maybe less than a meter per second or a meter per second. Now you can see retracted downwards, and now it's pulling up at that particular speed. In the background, you can see my video camera replaying the actual test, and you can see that we captured the complete test, or the test completely. And now basically what happens afterwards is that we of course couple the load and strain together so that we can construct a stress strain curve. Slightly faster test, or actually not slightly, it is a faster test. This is 500 strains per second. So now we're getting to if you go to that video that I mentioned earlier, it talks about the introduction, and then also it talks about an actual demo, how to mount the sample and what to pay attention to and so on, and then how to set the parameters of the machine and then perform a good test. Now, in the last part of this webinar, I wanted to go over some examples of good stress strain tests that were done at different rates, from the intermediate all the way to the high rates, above whatever, 200, 300, 400 strains per second. So let's take a quick look at some of these curves. This is again the same raw data that I showed earlier for 50 strains per second, and that's why I put that statement there, that you can obtain some good stress strain curves up to about 100 without strain gauging. It depends on the material, to be honest, so not always successful, but with some optimization and with good material, it could work. This is another example of a stainless steel grade, very high ductility material, obviously 50-60% strain in terms of ductility, but in terms of stress strain response, we got very good response without having to strain gauges. Of course, you can see the waviness of the stress strain curve, but that is not a problem because you're feeding this ultimately to a finite element model. So you just need the curve to be as good as this curve in order to represent the stress strain relationship. So long there are no big, let's call it fluctuations in the stress strain curve that represent ringing, then you should be fine. Now, when we go to higher strain rates, 500 strains per second, in this case, this is an aluminum alloy, I think, and you can see the stress strain response was fantastic. We have lots of data points, and every single circle is a data point that came from the IC coupled with the load measurement from strain gauges. And you can see an overlay over the Kistler load data. The same exact material repeated 3 times, and this is just to demonstrate that you can get repeatable results over and over if everything is done correctly. And you can see even the response of the Kistler load washer was almost exactly the same over the 3 times, even though, again, the data, the black curves are not really usable here. And so we just basically use the strain gauge data. This is another example of a high strain rate test that was done at 750 strains per second on an advanced high-sense steel with high ductility. And I try to always show it with the data points themselves, without filtering whatsoever. So you can see the density of data that was obtained for this strain rate. And this is another example of, if we do it correctly with DIC, we can overcome the problems of DIC, the general problem that I mentioned earlier, that we don't have enough data points at those strain rates because of the limitations of high-speed cameras. In essence, yes, it is a big problem, but it can be alleviated, and this is an example of it. This particular curve had over 150 points, or 100 and some points, which is more than sufficient to describe the stress-strain response of the material. Now we go to maybe more comprehensive examples. This is a full set of curves for a stamping application. This is a progressive stamping material, and so you can see the strain rates going from 0.5, maybe upper quasi-static, to 50. This is almost upper intermediate to early high rate. And so you can see the 4 sets of curves right on top of each other, high repeatability, good quality curves. The serrations in the curves are not driven by the test itself. This is actually material response, because you can see the blue curves are very smooth, but at higher rates, this material that exhibits this response as the deformation rate increases. And you will see some of that in some of the aluminum alloys as well. Another set of curves at higher rates. This is a set of curves that was generated for a material that was used for crash applications or crash simulations. And the deformation rate went from, or we covered it from 1 to about 750 strains per second. Another example of full set of stress strain curves from 001 to 1000. This is usually the full range from min to max of such systems, high-speed hydraulic systems, and you typically don't need more than 1,000 strains per second to represent materials for automotive applications. And last, I think not least, complex advanced high-strength steel with a certain manganese content, which usually drives a very complex behavior, change in the strain hardening behavior. As you can see, the blue slash purple curves are the ones corresponding to the quasi-static deformation or the quasi-static rate. And then as we increase the strain rate, you can see totally different stress and stress level, and also ductility level, and also strain hardening level. Very complex material behavior that was captured at different strain rates. Now we wanted to take another look at comparison with the literature. And the objective here is to try to hopefully show you that the stigma that is presented in the literature can be broken in terms of the quality of the stress strain curves that can be obtained with servohydraulic systems. And I just took some of the data that is open in the literature, basically, to compare directly or indirectly. For example, we got some really nice curves on the right-hand side from the literature for different types of steels that are 1200 megapascal level. So we decided to compare it with 1200 megapascal level steel that we have good results for, to show, for example, at 500 strains per second, the red curve is relatively very smooth, actually. Do not forget something we mentioned, and if I didn't mention it clearly, I would like to mention it again. For high-rate testing, you should avoid the elastic region. You will not get any reasonable results there because of limitations on the accuracy of your strain measurement. DIC is fantastic. It just cannot solve these problems easily. So don't, what we always tell our clients and also our colleagues is that don't focus too much on the quality of the stress strain curve in the elastic region for high-speed testing. You should just focus on the plastic. And that's where the curves quality basically should be good. This is a nice comparison with data obtained by Kolsky bar. So on the right-hand side, this is a DP980 standard workhorse material for the automotive sector. It's a 1,000 megapascal grade, basically. And the curve on the right-hand side was obtained with Kolsky, split Hopkinson bar, which is known to be high-quality data anyway. And you can see the curve is good. This is typically hard to achieve with servo-hydraulic machines, but on the left, we show you an example of a similar material, not necessarily the same DP980, but at least it shows a DP980 test that was done with a servo-hydraulic machine, and you can see the quality of the curve is as good, if not better, than the Kolsky bar. And here's another example with Kolsky bar data from another study that was published in the literature. And you can see the same curve is relatively smooth. In fact, I would say even smoother than some of the curves that were obtained with Kolsky bar at maybe slightly higher rates, but from a deformation perspective, it doesn't really make any difference. Statistically speaking, 500 frames per second and 1,000 frames per second, they're statistically not that different. A complex material, medium manganese steel. I got these results on the right-hand side from our previous results with my ex-PhD student. He tried with the system that was available to him. He tried to obtain the higher quality data at high strain rate, like 500 frames per second. You can see the curve wasn't up to scratch, but ultimately we took the same exact material and we tested it with an optimized system, optimized basically approach, and we got much better results. That being said, I wanted to highlight here is that what I wanted to highlight here is that not always can you obtain perfect or near perfect results at 500 frames per second or 1,000 frames per second. And this is an example of it. The red curve, you can see some wiggles and some fluctuation at the beginning. Yes, it is the result of some ringing, which couldn't be alleviated completely. The curve is still fantastic for 500 frames per second, but this is also the result of the material itself. From our humble experience, if we deal with materials that have a YPE, which clearly this material exhibits it, even at quasi-static conditions, you can see it very clearly. We tend to notice this all the time. If we have a YPE, it is almost impossible to avoid those fluctuations, smaller fluctuations. They're not as large as ringing fluctuations or sort of waviness. So they will always be there. And we've learned to just accept them because that's the best that you can get with such materials. This was a stainless steel. Beautiful curves were obtained at 500 frames per second, as you can see on the left-hand side. Very nice, smooth curves, no problems, no ringing, or at least no notable problems at high deformation rates. And I wanted to compare this to the right-hand side curve that was obtained with a Kolsky bar setup. And obviously, I'm trying to highlight here that with Kolsky bar, we were able to get to about, we were able to get to about 20 strains, 20% strains. Again, that's the limitation of a Kolsky bar with the wave ending before the sample is completely deformed. While on the left-hand side, you can see we got to over 65% deformation in one shot. Last couple of examples, the TWIP 800 material. This is a high-strength steel, relatively complex material because of its manganese content. But you can see the curve quality on the left was very good. And last, I think, example I have is for a mild steel. This is another example I chose to present to also demonstrate that for some materials, you can do all you want and it will not be as great as you wish. And that is one material that was very challenging for us. You can see our curve is not the quality of the other curves that we obtain for other materials. And that is a problem with certain materials. Mild steel was, this sample was very soft, very thin. This is a 0.6 or 0.7 millimeter thick sheet. So we have a lack of stiffness here. So we tried to eliminate ringing there, but you can see a big dip in the middle of the curve that we couldn't eliminate. That being said, when I compare it to the results from a Kolsky bar, which again, Kolsky bar is known to produce very high quality results, and you can see on the right-hand side, you still have the same issues. The curves are not smooth, and on top of that, the curve terminates after 20%. After 20%, it just descends down, which is basically the end of the wave. So at the very least, we were able to obtain a better quality curve with the servo-hydraulic system, and also all the way to failure to about 50%. Aluminium was shown earlier, and this is just a comparison with the literature and how we can obtain basically really good results for some of the advanced aluminum alloys as well. not only my last two slides here are just basically snapshots from our future webinar that is focused on DIC. Again, reminder, we talked today about how to fix the problem with the vertical axis, which is the force in high-speed testing or intermediate and high-speed testing. But DIC plays an important role. This is how you can control the x-axis of your stress strain curve. And so, um, since we're not going into the details here, I just wanted to show that a sneak peek actually at the future webinar of what can be done with high-speed testing, how can we improve our high-speed data in regards to DIC measurements. And these are two examples I picked. One of them is at a strain rate of 100. And you can see direct coupling between the force measurement and the DIC video that's running on the top. We were able to obtain good correlation for this material. This is a 1200 megapascal steel, third-gen steel, tested at a relatively high rate. And you can see correlation all the way to the fracture point, no loss of correlation. And very important to us when we do such tests is we look at the linearity of the strain time curves because you want them to be as linear as possible. You want the deformation to be balanced. Another example at much higher rate, 750 strains per second, you can see the raw data. It's still relatively smooth, very smooth curve for such a speed. And the video shows that DIC was also successful in terms of correlating the images all the way to the fracture point, and on the at the bottom right corner, again you can see the curves are linear, which indicates a nice balanced deformation for this material. That was my last technical slide. To conclude what we've done today, we have talked about intermediate to high rate data. And the importance of adding this to the quasi-static to complete the picture for material deformation. We've shown that there is a critical need for such data, mainly in tension, but some other modes are also necessary. This data is needed for at least lightweight materials for the transportation sector because of obviously the need to form them and then to check for their crash performance. This is not only true for metals, it's true also for composites and polymers. We talked a little bit about the different approaches, and we focused on the two most important approaches for generating such data. And ultimately, I focused on the approach that we personally chose to pursue, which is the high-speed servohydraulic testing approach. These systems offer many advantages over the split Hopkinson bar. However, they come with challenges, but we've demonstrated that the technical challenges can be addressed, alleviated, not necessarily completely removed, but in some cases you'll get fantastic curves, and in some cases you will get near perfect curves, and sometimes better than Korsky bar. So there is a lot of potential for these systems, and one of the things that we like about them, again, is the fact that they can generate curves that cover a wide range of strain rates that is needed for such industries like the automotive and transportation sectors. We showed, we discussed the technical challenges. We showed some of the examples of curves that were obtained with these systems, some steels and some aluminiums. And in the future, we will have separate webinars because the challenges are technically different for other materials. And we wanted to dedicate another webinar to talk about high-speed testing of polymers, composites, and even thin foils. We have similar challenges with metals. Let's call them system challenges, DIC challenges, but then we have another set of challenges, and that's why we decided to focus this webinar on automotive metallic materials, and then in the future we will talk about the same set of challenges and other challenges when we go to polymers and thin foils and composites. This was my last slide. I thank you again for attending this webinar. I hope it answered some questions if you had it. Please feel free to send us questions. I am putting here the email addresses that you can send questions to, and we will do our best to answer them. And we look forward to you joining us in future webinars. Thank you again, and have a nice day.